When determining the appropriate size for a transformer, a critical factor is applied to the total calculated power demand. This factor, which can be misunderstood, plays a vital role in ensuring the transformer operates efficiently and reliably without being oversized or undersized. The factor in question adjusts the total connected load to account for the fact that not all loads operate simultaneously or at their maximum rated power. It is essential to differentiate between several related concepts to accurately understand this factor. Firstly, the demand factor is the ratio of the maximum demand of a system, or part of a system, to the total connected load of the system, or the part of the system under consideration. The demand factor is always less than or equal to 1.0 because the maximum demand cannot exceed the total connected load. Secondly, the load factor is the ratio of the average load over a designated period to the peak load occurring during that same period. The load factor provides insight into how consistently a load is used over time. Thirdly, the diversity factor is the ratio of the sum of the individual maximum demands of the various subdivisions of a system to the maximum demand of the entire system. The diversity factor is typically greater than 1.0 because it reflects the fact that individual loads do not peak at the same time. Fourthly, the utilization factor is the ratio of the maximum demand of a system to the rated capacity of the system. The utilization factor indicates how fully the system's capacity is being used. Given the context of multiplying the total calculated power by a factor less than 1.0 to determine the transformer size, this factor is most closely related to the demand factor. The demand factor recognizes that the total connected load represents the sum of all individual loads, but in reality, not all of these loads will operate simultaneously at their maximum rating. Therefore, applying the demand factor to the total connected load provides a more realistic estimate of the actual power demand that the transformer must supply. For example, consider a commercial building with a total connected load of 500 kVA. If the demand factor is 0.4, this means that the estimated maximum demand on the transformer is 500 kVA multiplied by 0.4, which equals 200 kVA. In this case, a transformer rated at 200 kVA would likely be sufficient to supply the building's power needs. However, several considerations are crucial when applying the demand factor. Firstly, the demand factor should be based on empirical data or established industry standards. It is essential to have a reliable basis for determining the appropriate demand factor for a given application. Using an incorrect demand factor can lead to either oversizing or undersizing the transformer, both of which have negative consequences. Secondly, the demand factor can vary depending on the type of load, the occupancy of the building, and other factors. For example, a hospital will typically have a higher demand factor than an office building because hospitals require continuous power for critical equipment and life support systems. Similarly, a manufacturing facility with heavy machinery will likely have a higher demand factor than a retail store. Thirdly, it is essential to consider future load growth when selecting a transformer. If the building's power demand is expected to increase in the future, the transformer should be sized to accommodate this growth. In some cases, it may be prudent to select a transformer with a slightly higher capacity than currently required to provide a margin of safety and accommodate future expansion. Fourthly, the transformer's efficiency and thermal characteristics must be considered. Transformers generate heat as they operate, and this heat must be dissipated to prevent overheating and damage. The transformer's efficiency is the ratio of the output power to the input power, and the difference between the input and output power is lost as heat. A more efficient transformer will generate less heat and can operate at a higher load without exceeding its temperature rating. Fifthly, the transformer's impedance should be considered. The impedance of a transformer is the opposition to the flow of alternating current. A transformer with a lower impedance will have a higher fault current, which means it can deliver more current during a short circuit or other fault condition. This is important for protecting the electrical system from damage and ensuring the safety of personnel. Sixthly, local electrical codes and regulations must be followed when selecting and installing a transformer. These codes and regulations typically specify the minimum requirements for transformer size, installation, and protection. Failure to comply with these codes and regulations can result in fines, penalties, and even legal action. Seventhly, it is important to consult with a qualified electrical engineer when selecting a transformer. An electrical engineer can perform a detailed load calculation and determine the appropriate transformer size based on the specific requirements of the application. They can also advise on other factors such as transformer efficiency, impedance, and protection. Eighthly, the power factor should be considered when sizing a transformer. Power factor is the ratio of real power to apparent power in an electrical circuit. A low power factor can increase the current flowing through the transformer, which can lead to overheating and reduced efficiency. Power factor correction equipment can be used to improve the power factor and reduce the current flowing through the transformer. Ninthly, the harmonic content of the load should be considered when sizing a transformer. Harmonics are distortions in the sinusoidal waveform of the alternating current. Harmonics can be generated by nonlinear loads such as electronic devices and can cause overheating and other problems in the transformer. Transformers designed to handle harmonic loads, known as K-rated transformers, are available. Tenthly, the altitude and ambient temperature of the installation location should be considered. Transformers are typically rated for operation at a specific altitude and ambient temperature. If the transformer is installed at a higher altitude or in a hotter environment, its capacity may need to be derated to prevent overheating. For instance, let's delve deeper into a practical example to illustrate the application of the demand factor in transformer sizing. Imagine a multi-tenant office building where various businesses operate with different electrical demands. The connected loads include lighting, HVAC systems, computers, and other office equipment. Firstly, we need to calculate the total connected load by summing up the power requirements of all individual loads in the building. Let's assume that after careful calculation, the total connected load is determined to be 800 kVA. Secondly, to accurately size the transformer, we need to consider that not all of these loads will operate simultaneously at their maximum capacity. This is where the demand factor comes into play. The demand factor is an empirically derived value that represents the ratio of the maximum demand of the building to its total connected load. This value is typically based on historical data, industry standards, and the specific characteristics of the building and its occupants. Thirdly, in this example, let's assume that a demand factor of 0.6 is deemed appropriate based on the type of office spaces and the typical usage patterns. This implies that, on average, the building's maximum demand is only 60% of its total connected load. Fourthly, to determine the appropriate transformer size, we multiply the total connected load by the demand factor. This calculation yields a maximum demand of 800 kVA multiplied by 0.6, which equals 480 kVA. Fifthly, this result suggests that a transformer with a capacity of 480 kVA would be sufficient to meet the building's power needs. However, it is crucial to consider additional factors before making a final decision. Sixthly, we need to account for potential future load growth. If the building is expected to add more tenants or increase its electrical consumption in the coming years, it would be prudent to select a transformer with a slightly larger capacity to accommodate this growth. Seventhly, we should also consider the transformer's efficiency. A more efficient transformer will generate less heat and reduce energy losses, which can lead to significant cost savings over the transformer's lifespan. It is advisable to choose a transformer that meets or exceeds industry standards for efficiency. Eighthly, the transformer's impedance should be carefully evaluated. A lower impedance transformer will provide better voltage regulation and improve the building's ability to handle short-circuit faults. However, it will also result in higher fault currents, which must be considered when selecting protective devices. Ninthly, we must comply with all applicable local electrical codes and regulations. These codes typically specify minimum requirements for transformer size, installation, and protection. Failure to comply with these codes can result in costly penalties and delays. Tenthly, consulting with a qualified electrical engineer is highly recommended. An experienced engineer can perform a detailed load analysis, taking into account all relevant factors to determine the optimal transformer size and configuration for the specific application. In summary, the demand factor is a critical element in transformer sizing. It allows us to accurately estimate the maximum power demand of a building or facility and select a transformer that is appropriately sized for the application. By considering all relevant factors, we can ensure that the transformer operates efficiently, reliably, and safely, while also minimizing energy losses and costs.